Okay, let's do another example problem here. Let's start off just remembering, okay, for a moment. So let's just remember for a moment here that we had the electric field of a ring of charge. So it was a ring of charge and we're some height z above the ring of charge. And so the question was, what was the electric field right there? And we had calculated that the electric field there is only in the z direction, and that's going to be KQZ divided by z squared plus r squared to the 3/2. And so that was that was going to be the electric field, and it's going to be in the z direction. Okay. Now what I want to do is imagine we've got a solid disk and we're some distance z above the center of the disk. And so I want to know, what is the electric field there? Well, the same argument holds that wherever we are, there's going to be something on the other side that balances it. So by symmetry, we know that the electric field, whatever it is going to be some function of something, probably z, and it's going to be probably other stuff too, and it's only going to be in the z direction. So we can just sort of say already by symmetry, we know something about this, okay? And so that's your first step, okay? And so we know that all the other components cancel out, so all we have to do is integrate the DEZs, okay? And that's going to give us our electric fields. How do we get DEZs? Well, what we can do is we can imagine that we've got a little disk of dq. So the entire disk has some charge q spread out the whole area. So it's going to have some surface charge density, sigma. And so this little dq is going to be, imagine that's going to be a little ring of charge there. That makes an electric field. There's another little ring of charge, another ring of charge, another ring of charge. So all we really need to do is we've got to integrate over the dE of the ring of charge, and we integrate from the center out to the radius of the disk. Okay. And so that's really all that we have to do. Okay. And so that sounds pretty simple. Okay. So that means it's going to be the integral of k sub e z dq divided by z squared plus r squared to the 3/2. Okay. And we're integrating from 0 that's dq, not dz, dq. And so integrating from 0 up to big R. Now the problem is, what's dq? dq for our disk here, dq is the charge on that little ring. So what's the charge on the ring? Well, that's going to be sigma times the area of the ring. Now what's the area of the ring? Well, it's the distance around the ring, which is 2 pi r, times the thickness of the ring, which is dr. Okay. And so we would then say, okay, so that means that is going to be, and then all that times sigma. So that's going to be the area of the ring right here. So this is the area of the ring, okay? The distance around, 2 pi r, the thickness, which is dr. Okay, and so that's going to give you the area of this little differential ring. So if we put that in, so this is now going to be integral, okay, of kq or ke, okay, so integral of Ke Z sigma 2 pi r dr divided by z squared plus r squared to the 3/2 integrated from 0 to r. Okay, so the nice thing about this is that a lot of this stuff, k sub e, the z, the sigma, the 2 pi, all of that is constant and it comes out of the integral. So now just integral 0 to r of r dr divided by z squared plus r squared to the 3/2. Okay. All right. So now we look at that and we say, well, how do we do that? Well, if we move the 2 back in there, k sub e z sigma pi integral r 0 to r of 2r dr over z squared plus r squared to the 3/2, you notice that now the numerator is the derivative of this thing down here in the denominator. Okay, so that means that we can then say that when you do the integral, okay, then this is going to be equal to sigma z, okay, k sub e, sigma z, we do the integral, this is going to be equal to minus 2 over square root of z squared plus r squared evaluated at 0 and r. You know, because now we went from the 3/2 to the 1/2 divided by 1/2. Remember, this is how you do this integral. And so so now we've got that, and we say, okay, fantastic. So this is going to be 2k sub e sigma z. Okay, then we plug in the numbers right here, and that ends up being 1 over square root z squared plus r squared minus a negative, so plus 1 over 1 over z. Okay. Now you look at that and you say, well, wait a minute. Wait, I'm sorry, I lost a pi in here. Okay, so lost a pi in there. Okay, so now we say, well, wait, that's pretty straightforward, because now we know this is going to be equal to 2 sigma z pi, and that is divided by 4 pi epsilon naught, because after all, that's what the k sub e is. And so now minus 1 over square root z squared plus r squared plus 1 over z. Okay, that pi goes away, and so we end up with the electric field as sigma z divided by 2 epsilon naught. Minus 1 over square root z squared plus r squared plus 1 over z. Now, that's going to be the electric field some distance z above this r. But what if we make an assumption here that it's a very big disk? Now, what do I mean by very big? I mean, just mean the r is much, much bigger than z. So if R is much, much bigger than Z, that means that Z is effectively going to be pretty small. Okay. And so in that case, this first term would be pretty close to 0. Okay. And so then we would have that the electric field is sigma Z over 2 epsilon naught times 1 over Z. The Z's cancel, so the electric field can be sigma over 2 epsilon naught. Okay, now that's a really interesting thing, because that means for our disk, as long as our Z is close to the disk, in other words, as long as Z is much, much less than R, okay, that means that the electric field is going to be approximately sigma over 2 epsilon naught. And that is a constant, because all the Z's have now canceled out. The R's have canceled out. The only thing that matters is, well, the only thing that matters is sigma. So what is the charge per area? And so you end up with this constant sort of value right here. So that means everywhere above those plates is a constant value. And this is how you typically get a constant electric field. You can take two metal plates, make one of them positive, one of them negative, and the electric field everywhere between the two is going to be constant between the two. And if they both have the same sigma on them, then the electric field is going to be equal to sigma over 2 epsilon naught. Okay. And so that's basically how you do this. And it's going to be a fantastic tool for us later on to actually find, the electric field. Okay. Now, the other thing, I talked about this as a disk. What if it was a giant square sheet or rectangular sheet? Well, if you're really long ways away, so if R is much, much greater than Z, then it doesn't really matter what the edges of it look like. So for all of this, as long as R is much, much greater than Z, if it is flat, any kind of flat disk, then the electric field is going to be sigma over 2 epsilon naught. And it's going to be directed away from the surface. And so that is the electric field near a surface of charge. Okay. And so with that, we'll do a couple of examples.